So I will talk about climate change, solar activity, and realistic impact and risk assessment for the 21st century. And I believe this is a very interesting topic because it faces some of the most important issues that society would like to know about this issue right now. Okay, so the main issue is to understand how much will the Earth warm. Because this is what evaluates the risk. So if I would like to assess the risk, I need to know how much and how fast the Earth warms in time. So first of all, we have seen in the media, we have seen a picture like this. So there is a lot of so-called climate alarmism, these pictures actually talk about weather conditions, not really climate change conditions. So climate by itself is something that changes very, very slowly in time. So we cannot just see it very easily. So we need statistical tools for detecting climate change. So we need not to mistake climate change with weather condition that changes continuously in time. Climate, as you see in this picture, has always changed in time. This picture is the climatic history of the Earth. And what you see here is that the temperature of the Earth has always changed a lot in time. So what you see here, you see, first of all, you see periods occurred several hundred million years ago, where the temperature was much, much higher than today. So we are talking about 10, 12, 14 degrees above today. And what we see here is also large oscillations, so very large oscillations. These oscillations have actually a period of 150 million years. Then there are other long oscillations, like 32 million years. Then if we look at this period, this is between 20,000 and 1 million years ago, we see these large oscillations. These oscillations are due by a combination of orbital oscillations, or the orbit of the Earth involving the eccentricity, the obliquity, and the precession of the axis, of the Earth axis. And we see some period like the Mian period, that is this peak here. This is the last interglacial period, where the temperature was clearly higher than today. So it was much higher than today. Then we have this period, very cold period. So this is where the glacial period, and this is the last glacier, and then the temperature went up, and there was the Holocene. This is the last 10,000 years, so the Holocene. During the Holocene, this record is very complex. We see a lot of oscillation that we are going to discuss briefly in this talk, like 1,000 millennial various millennial oscillations, secular oscillations, decadal oscillations, multi-decadal oscillations, and so on. And these oscillations are believed to be solar induced, and some of them could be lunar induced. So climate is very complex, but it is also made of several oscillations. And we need to understand that these oscillations if we would like to understand climate change, okay? Now, let's go back to what everybody is talking about. So this is the temperature of the Earth during the last 150 years, so since 1850. You see the temperature went up by about 1 degree. And the main issue is whether or not this warming is due to humans or to nature. Okay, so nature changes climate, so we know that. So let us see very briefly how this record is interpreted currently by the IPCC. And it is interpreted using climate models. These models use a set of forcing. These are the forcing adopted by the models. So this forcing are assumed to be able to change climate, to change climate. Many of these forcing are labeled as anthropogenic, so like CO2, for example, but there are many others. So we have a total anthropogenic, that is the sum of all these components. Then some of them are believed to be natural, like, for example, the solar effect, the solar contribution. And what we do with the models. So what the IPCC proposes is to use climate models for interpreting the record. And the climate models are run in two different ways. There is one set of simulations where only the natural forcing are used in the models. So natural forcing means solar and volcano forcing, no? And what we find, what the models find, is that in this case, the climate should have been constant, okay? Should have been constant since 1850, completely constant, as you see here. Then the models are run by adding all known forcing, including, of course, the human anthropogenic forcing, plus the natural. And what the model does is to produce this warming, to produce this warming. So the IPCC concludes that according to these models, 100% of the warming since 1850-1900, the pre-industrial period, is caused by human emissions. This is what the IPCC claims. This is why we are talking about anthropogenic global warming. It is not a percentage. It is practically 100% of the warming since this period is due to human forces, to human-based emissions in particular. The problem with this argument, however, is that there is a little problem because according to the scientific method, the simulations must be tested against the observations. And although here we have a comparison between observed and simulated climate change, here we do not have the observed climate change. We only have the simulated one. And according to the scientific method, this is not enough. Okay, so practically to have the observed data, we should have an Earth without humans. We do not have an Earth without humans from where we could get the data to validate the models. Therefore, this picture may be reasonable only if the models are already validated, but the models are not already validated, as we will discuss later. Therefore, this picture is misleading, is a violation of the scientific method, okay? Okay, so CO2 is blamed to be, of course, this poison, this big problem of humanity. But what we know from many studies is that CO2 is increasing, is greening the Earth, because CO2 is food of plants, is not really dangerous gas. Okay, it is climate. It might change climate. We will see now how. Then what the IPCC does? So why there is the alarm? Why there is the alarm? The IPCC does the following things. Okay, it uses models to try to simulate the climate change of the past, and then it continues with other simulations, which are this colored curve. These colored curves are produced by the models, are projections produced by the models under different scenarios, emission scenarios, which have this name, SSP1, SSP2, SSP3, SSP5, and so on. So we have different scenarios that implies different amount of emissions. And what we see here is that the temperature will go up. And what it is believed, what it is assumed by the IPCC is that if the temperature will rise above 2 Celsius 2 Celsius, this is 2 Celsius target, 2 Celsius, then a lot of systems will start to be vulnerable to climate change because of the fast changes that occur. So water security, coastal community, and so on, natural ecosystems, and so on, will start to suffer if there is such a rapid climate change by practically 250, right? So what people would like to do is to remain below the 2 Celsius, so in this area where we can adapt easily, and therefore there will be no big problem, big issue. But to do this, we need to apply the SSP1 scenario, which is as the scenario, the zero emission scenario. So by 2050, we need the net emissions should be zero. Okay, net emission means that we can emit CO2, but then we need also to absorb CO2, and the two things must balance. Okay. And the problem, what is the problem? The problem is that people are not doing this. Nations are not doing this. Nations are doing this other, SSP2, which means that we will cross the 2 Celsius the target by 2050. And this is not enough. Okay, we need to do more. This is what these people are telling us. These young people are telling us. We need to do more to save the world, because we will not save the world if we continue to do what we are doing right now. So Europe would like to save the world. So we have this 2050 long-term strategy, zero emission by 2050. But people don't like the policies, because they are concerned about the cost, the economical cost, which is huge for this policy, for this point. And this is why I would like why this issue is so important for society. Now, I am a scientist and I am not a politician. So the questions that I would like to ask and to answer is this one. Is the alarmist narrative based on sand or rock? This is the question. This is the basic question. So let us discuss the various issues that we are facing. Now, the projected warming for the 21st century strongly depends on three main points. Well, first, on the shared socioeconomic pathway. So we have seen that there are several pathways, SSP1, 2, 3, 5, and so on. And here you see the simulation of the models. So you see that the future warming will depend on the scenario, okay? So it will be very different in the simulation. The second point is that the issue depends on the equilibrium climate sensitivity of the models. Here we have this column is the equilibrium climate sensitivity. So this means how much the climate is supposed to change, so to warm, if we increase CO2, okay? So these are the degree Celsius for doubling the CO2 from 280 to 50, 60 parts per million. So we see here that colors are different. So the models with low climate sensitivity produce less warming. The models with a high climate sensitivity produce more warming. So we need to decide which models is credible, because the difference is huge and therefore it's important. The third issue is that whether or not these models are reliable. We do not know that. So we need to determine it. Are they reliable? We need to do science, not games, okay? Play a PlayStation game, okay? So we need to do science. We need to compare the models with the nature, and the two things, the predictions of the model must agree with nature. If not, the model is not validated. This is it. So let us discuss the issue. Which issue is realistic? Which issue is realistic? Well, it is not my paper. This is what you find on Nature, and there are the many people now are telling us that the only scenario that is really realistic is the SSP2 4.5. So why? Because we have this is what people state are doing. These are the current policy. They are following this scenario here, that is the SSP2. Okay, so these other scenarios that the IPCC have used are considered highly unlikely and unlikely. So it is not me who say that. You find it is the economists who are telling this. Okay, so these are economical issues. Economists say these are not credible. These are completely crazy. Then this is the scenario, zero emission scenario. So you see it goes down. But people are doing this, okay, which do not save the world, according to the IPCC. Now, this is not me, it's not just me. Also, the IPCC say the same thing, acknowledge that the likelihood of high emission scenarios such as 8.5 of SSP 8.5 is considered low in light of the recent developments in the energy sector. So it is not me, it's written in the IPCC. Studies that consider possible future emission trends in the absence of additional climate policy are approximately in line with the intermediate scenario, no? So 4.5, SSP2, so on. So the IPCC itself acknowledges that these are the realistic scenarios. The problem is that the IPCC simultaneously shows a lot of pictures where they use the 8.5 scenario. So they use the SSP5 8.5 scenario, as you see in this table, which is not realistic, but is very alarming, very alarming. And despite it is very alarming, the IPCC plots this kind of pictures where you see that many of the most dangerous issues, like you see here something very, very dangerous, do not change at all. So there is so what changes are the extreme heat, cold spell, so this stuff here. So there are things that may change related to climate change. So people are talking about these heat waves and so on, but many other things like hurricanes and so on will not change much. Okay, so this is what the IPCC itself says. So in any case, the 8.5 is not realistic. And therefore, because this is the realistic one, this estimate must be reduced. Issue number 2, which model could be realistic? So let us talk about the equilibrium climate sensitivity issue. Now, climate sensitivity, what is climate sensitivity? It's a CO2 warming plus the effects of the feedbacks, climatic feedbacks, okay? CO2 may produce more water vapor and less clouds, and this would produce more warming. This is what the models tell us that will happen. The problem, however, is that the models contradict each other. Each model, these are 40 models about, predict a different climate sensitivity, And we go from very low values, like these models here, that have a 1.8, 1.9 Celsius, which means that if CO2 is doubled, the warming will be just 1.8 Celsius. And we have these models that predict 5.6 Celsius for the same amount of CO2. So what I did is simply this is a huge uncertainty, which means the climate modelers are the first one who have no clue about what the CO2 is doing to the climate. There is this huge uncertainty due to the uncertainty related mostly to the feedback, okay, water vapor, clouds, and so on. Now, let us therefore divide this range in 3 parts. We have low sensitivity model, medium sensitivity models, high sensitivity models. And let us see which of these models perform better. And what we find in the literature is that the people are realizing that there is a hot model problem, okay? And here you see the name, some well-known name, Gavin Smith, for example, who, of course, is a very, is a proponent of the anthropogenic global warming theory, and he too acknowledges that there is a hot model problem. But the hot model problem is much worse than what Smith acknowledges, because, as I said, the models say that the climate sensitivity may vary between 1.8 and 5.8 Celsius. However, there was this paper, Sherwood, which tells us that the climate sensitivity very likely should range within 2.6 to 3.9 Celsius. This is what the IPCC has acknowledged. So the IPCC used this as the likely range, okay? But then there was this paper by Lewis that found a lot of apparent errors in Sherwood work. And Lewis proposed that the real climate sensitivity may be between 1.7 and 2.7, so it's much less than what is written here. I have also done several work on the topic and realized the same, that the equilibrium sensitivity should be less than 3, like Lewis, and very likely between 1.2, so it might be even at 1.2. Then there was a paper by Spencer and Christie who arrived to the same conclusion of mine. So it is the climate sensitivity appears to be important. This is a graphical representation. So in the literature, the climate sensitivity may vary in this range. This is what the model do. This is what the IPCC believes to be correct. This is what Lewis believes to be correct. This is me. This is Spencer. So we are on the. We found out that the climate sensitivity appears to be low, and this is the reason why it appears to be low. So here we have since 1980, we see the data, and we see the models. These are the high sensitivity models. You see that they are off to hot. We are the medium sensitivity models where, okay, it's hot, still hot. We are the low sensitivity models where it is clearly, it might be correct. So it might be correct. However, there is a problem here. So here is the same picture of here is the warming with the surface warming. We have the warming detected by the satellites. And what we see here is that this warming during the same period, so during this period, is less than what the surface are showing, which implies that if these data are the one really valid, as we will discuss later, then all models are wrong. This is essentially also the conclusions of Spencer and Christie. Critical issue number 3. Is there further evidence that the models may be physically incorrect? So there are some word bias. Okay, models may be incorrect. There are a lot of evidences that the models may be incorrect. This is what the IPCC publishes. Okay, so this is a paper of the IPCC. So they show here the models. This is the troposphere and stratosphere. So this is the warming in black of the data, the warming of the data in these periods that you see here. And these are the predictions of the models. And it is easy to realize that here the models have huge problems. So they are not really correct in predicting the warming of the entire profile of the troposphere in the tropics, above the tropics. And this is a problem for the models because they show a lot of warming, which is directly derived from the theory of climate change based on CO2 increase, and the data that do not really show this work. So there is a problem, very serious problem in the model. The data, however, may be also problematic because the data on the land, in particular those on the land, may be affected by undetected urban heat island effects. So these are some my evidence that I have collected. So, for example, this is a paper where I compared the urban and rural stations. So you see that the rural stations have a warming much less than the total station. Okay, so they show less warming. This is the comparison between the land station The surface station and the satellite station WACA MSU. You see that the blue curve is the satellite has less warming. This is a comparison between the ocean and the land vision. So you see that satellite and data on the ocean more or less coincide, but on the land there is a big difference, okay? This is a reconstruction of the temperature with proxy from 3 rings against the temperature measured with the thermometer in the same region. You see that there is a huge difference. So it appears that there is some problem, some warming that is not detected by satellite, not detected by the trees, and so on. Then there is also a way how the models has been treated in time. In the last 10 years, we went from reconstruction like this blue line, which was the head CRUT3, where there is this pause, and then little by little the models, the data were shifted up, okay? They were shifted up by modeling data and so on. So you see that say something strange that is happening here, okay? So they are shifting up, so the things must be discussed. Myself, I did some work on this topic, and I realized that there are many places of the Earth that show evidences of urban effects. Which are this red line. There is some region like this one where there might be some geothermal heat coming out, but okay, so there might be. So and it's obvious that here there are the cities. There's a city here, and so on. So we see many places some cities. So this is the red things in China, and so we see some problem. Okay, we see some problem, and the difference between rural station and general stations is huge. So we can imply that there is. Now, okay, now let's go back to see other problems in the models that reveal problems in the models. These are another picture of the IPCC. Here you have the data. The black data are the data as they are reconstructed by pages 2K, which is one of the valuable reconstructions. I personally don't like much this reconstruction for other reason, but the IPCC like it much. So you put it here in this picture and many other pictures. The problem with this picture is that they also plot the simulation from the models, okay, which are these red curves. And these are the red curves that you see here. So it is easy to realize that the red curves is flat, is completely flat, as you see here. The data have a medieval warm period. It's a small warm period, not too warm, to be honest, but it is a warm period, okay? And a little ice age. So you see the warm period here, but the models are here. The models are below, much below this line. Therefore, the models do not get the warm period of the past. What this model produces is constant climate, a line with some volcano, and nothing else. So they do not produce any warm period of the past. So this is my picture on my paper where I show this problem. Models are here, data are here. So this might seem that the models agree with the data here, but here they don't get the warm period of the past. So perhaps it is evident the models have some mechanism that is missing here, and the same mechanism may be responsible of this warming, at least in part, but the model do not have it. Okay, so this is a problem. Models are supposed to reproduce the warm period of the past if they must be considered credible for interpreting correctly the warm period of the present. Okay, medieval warm period. Everybody knows, in particular from Irish, that there were the Vikings in Greenland. So I don't talk much about this. You know your weather. But this is on the Alps, for example, during the warm period of the Holocene, we have evidences of trees that were in places where now we have glaciers. So there are no trees, but here people find a tree under the glacier. So there was wood, it was warm. This was the pass of Susten in Switzerland. Today, no trees. Today, in the Roman period, it is believed that it was like this, with forests, with woods, because here we found pieces of rest of trees and so on. So trees were growing at much higher altitude, so that means it was warmer, much warmer than today. Okay, this is a reconstruction. This is the solar data. This is a reconstruction of the climate in Northern Hemisphere. There is a correlation, nice correlation. The warm periods, Roman, medieval, modern period, they correlate with high solar activity, cold period with low solar activity. Okay, fine. This is a temperature of Europe. This is summer European temperature. So what you see here is the modern warm period, little ice age, medieval warm period, some cold period during the previous period, Roman warm period with large peaks, larger than today. So that is what has been recorded in this paper. Okay, so these are in all Europe. This is what seems to have been the temperature. So this warming in perspective. So we had in the past other warm periods. So we are seeing a cycle, a 1,000-year cycle, for example. And we are seeing a correlation between climate change and solar data. So they have the same shape, essentially. This correlation between the solar data and climate change lasts for thousands of years. There are many, many papers to talk about this strong correlation. So you see this large cycle in the climate. This is the data, solar data. It's very similar. It's very, very similar. These are tropical glaciers in the Andes, very similar to the solar record. This is the Holocene with large oscillations. None of these are reproduced by the models because the models do this and then do this. Flat, okay? They don't get anything of this. This is again solar and climate data. Nice correlation for thousands of years with a cycle of 1,000 years. So many, many people. This is another paper in Europe. Modulation of the floods frequency in Central Europe during spring and summer on interannual to multi-centennial time scale. Strong correlation between floods and solar activity. Very strong, very strong, very thorough. There are many, many, many papers that show this strong correlation. This is a nice paper from Europe, from the Alps. So what people have found is a millennial cycle. So hot period, cold period, hot period, medieval period, cold period, Roman period, cold period, warm period, cold period, warm period, cold period, warm period. Say 1,000-year cycle found in many other records. So 1,000-year cycle is a cycle. Things are repeating. So people in this period, like Kepler, for example, predicted that there should have been some kind of warm period for Europe. Okay, they predicted it in 400 years ago. Okay, because they knew about this cycle. Those people already knew about a millennial cycle. It's written in the Bible. Now, if we look more carefully to the data and to this correlation between the solar-related record, like C14 and oxygen 18, that is a climate record, what people found, this is a paper by Neff in Nature, they found that there are many common oscillations. 1,000-year oscillation, 200-year oscillation, 90-year oscillation, 60-year oscillation, 46-year oscillation. And we know that all these oscillations are solar cycle, Eddy cycle, Debris cycle, Gleisberg cycle, 60-year cycle, 45-year cycle. All these are solar cycles. And what I demonstrated in this paper that I think that is very important, but it's my opinion, is that all these cycles are a special kind of resonances, gravitational resonances of the solar system due to the movement of the planets, large planets, Jupiter, Saturn, Uranus, and Neptune, who produce these oscillations. This red segment are the resonances, the orbital inequalities, what I call the orbital invariant inequalities that are special resonances. And you see here, they match these periodicities very clearly. Okay, so these cycles comes from the natural oscillation of the solar system, which seems to influence both climate change and solar activity. And this correlation between solar astronomical oscillations and climate change lasts also for the multi-decadal time scale. So here we have a record that collects the harmonics of the solar system, like the speed of the sun around the very center of the solar system. Here we have the global surface temperature. So we are analyzing the spectrum of these two records and compare them. So we find 60-year cycle here, 60-year cycle here, 20-year cycle here, 20-year cycle here, 13.8 cycle here, 13.8 cycle here. Then we have these two periods here. This is about 12 and 10-year cycle, which are actually compatible to the 11-year solar cycle signature, which is this one. Then we have this 9-year harmonics here, which is a lunar-related harmonic, and then we reappear a cycle 7.4 here and here. Then there is these and these and these. Here there is a little bit here. It's possible to see this is a cycle. There's another cycle here, a little bit. It's not very clearly, but there is. So all oscillations in global surface temperature are found in the space, in the oscillations of the solar system. These are the short range oscillations, while these are the longer range oscillations. And I developed these models of solar activity that is, and now I'm improving it a little bit. You find that these models based on the natural oscillations of the solar system and of the sunspot cycle. This model is able to produce a 1,000-year cycle, okay, 1,000-year cycle. It is able to produce these peaks, this cycle here, which matches right well the peaks found in the temperature. There are little peaks here that are matched these periodicities. You see better here. The comparison between my model in red and the data, the temperature data. You see that there is some kind of correlation. Now there is this, the model was predicting a low climate, low solar activity. That is what has been more or less observed. We are more or less here now. So we are seeing this kind of behavior that predicted by my model. This is a 6-year cycle, this 6-year cycle, this is around the 40s, so 50s, so this is 1,000, and then something like this. So this is a modulation. Now, why do the models fail to produce a mediator period? Okay, there may be total solar irradiance force, because we have seen that the data matches the solar record. So perhaps the models are using wrong total solar irradiance force. Or there might be additional solar forcing not related to the total solar irradiance force. So let us first of all address what the models of the IPCC do. The models of the IPCC make a strange choice. So in the literature, it is not really known what the sun does. There are a huge amount of solar records that has been constructed by different people. Some of them have a very large variability, others have a very low variability, And the models of the IPCC, they use this forcing that solar, this is very flat. Of course, if you use a very flat solar model, you get a flat result for the past when you do not have a CO2 forcing. But as we have seen before, this implies that you are not able to predict the medieval warm period and the other warm period of the past, whose cycles match solar record. So the sun cannot do something very, so cannot change so little, must change a little bit more, okay? They must change more likely something like this, but it cannot be really so easy. Now, the problem with the solar problem is very big, because it is important to realize that many models like this one that show very little variability as based on this reconstruction of the observed total solar irradiance from satellites, which show practically flat behavior. What people do not know, what people do not often know, is that this reconstruction is made using not the original total solar irradiance measurements that were published by the experimental teams, okay? These are the data published by the experimental teams. What this model does is to alter this data. In particular, see this data, this Nimbus data. This Nimbus data during this period went up. And these are the data from Nimbus, and you see here that it goes down. So what they did is to alter this data. They put them down because they claimed that to be wrong with this data, but there's no strong evidence. I proved in many of my papers that question this trend. So if you build a composite using the original data, the real data, these are not real data, these are altered data. If you use the real data, you get something that is going up. This is the Artin composite. So you get something that goes up and then goes a little bit down, and then, okay, it may change a little bit. But you see something that is variable, it's variable sign. So this kind of reconstruction may suggest that solar activity may have changed in the past, as many other studies would suggest. And also the climate study would suggest, because as I told you, I showed you, many studies show a strong correlation between climate and solar record, and this cannot happen if solar activity is practically constant, okay? So the IPCC uses this, but the sun might have done something like this, much bigger variation. These are other studies that show different reconstruction of solar activity. And here you have this record, this purple record is the one used by the IPCC for the long reconstruction. It's a Satire M. That is why that goes back for 1,000 years, and it's very flat, as you see here. So with these models, solar model, the climate are not able to get any of the climate warm period of the past, which suggests that this model is wrong for bad reason. What I did here is to, I combined several of these records, solar records. I produced this reconstruction of solar records. These are the records used by the IPCC. This is a volcano forcing. This is the anthropogenic forcing. And what I found out is that if I use the same technique used by the IPCC, essentially we found out that the solar activity is not really important. You see here, solar activity is this is anthropogenic, this is the volcano. So, so practically, if you use the logic of the IPCC, you get only the anthropogenic forcing as the dominant forcing. But if you adopt a different logic where you assume that you assume a different solar forcing, first of all, and then you assume that the climate system might have a sensitivity to solar changes different from volcanic changes, because there might be some other mechanism. Then you may also find out this result, where this is solar forcing, this is anthropogenic forcing, this is volcano. And this reconstruction fits the data much better than the models. So these are the models, okay? So they don't get this cooling here, they don't get this cooling here, they don't get well this warming here. They continue to go up while the temperature goes down here. So there are here they go too hot. So this is a model using my second approach, where we use different solar forcing. We assume that the climate system is hypersensitive to climate change, and we find a much better match. Okay, so their models, in my opinion, are strongly underestimating climate, and the solar may have strong effect on climate because there may be other mechanisms like cosmic rays. Cosmic rays are known to influence cloud systems. So these are the Bush decrease that occurs when there are max solar mass injection, strong solar wind. So cosmic ray is reduced, and then after a few days, the clouds are reduced. So this is what is observed. That's Vesmark who published this paper. So what are the impact and risks for the 21st century? So let us use these options. Low climate sensitivity, urban heat contaminated, consider natural solar variability. So using this possibility. So we have three options. So if we use the low climate sensitivity models, we get this scenario. So we get that the climate will go a little bit up to Celsius, not very slow, not too much. Okay, so this is the risk according to the risk and studies. If we assume that this warming is biased because the real warming is the one observed by the satellite, you need to rescale the models, and now we get something that is below 2 Celsius. So we get here, okay, this low Celsius. So there is no risk using the SSP2, which is the one that is credible. Okay, so we are not using the zero emission scenario. This is instead what happens if we include the climate oscillations. So the system, the models will produce this kind of oscillation. It's much better than the previous release. The models predicts this warming by 2100 using the SSP2 4.5 scenario. So we are below 2 Celsius degree. So no crisis, no alarm, using the SSP2 scenario. This is a summary of the results. This is what the IPCC say that happens according to various scenarios and using these models, which are what they believe to be credible. So the SSP2 is not sufficient to save the world. You see here that it's red here, okay? A little bit yellow. So we are above 2. So it's not safe. We will not save the world. We need to use the zero emission scenario to save the world because we need to stay here, okay? But if all I told you is correct, we end up with these three kinds of simulations that I showed you before. And therefore, if we use only the low sensitivity models, we are here by using the SSP2. So we are using the same scenario here, not this, but this. So we get this value instead of this. And so then we use, if the satellite are correct, we find this range. If the oscillations are used, we found this range. So you find here that on average we are below 2 or very close to 2, but in any case we are in a safe region. So on the base of this, I say that there is no alarm. Okay, so of course there will be some warming, but it will not be alarming. So it's a zero emission scenario. So this policy are not justified. Now, economical issue, also these are very important. Very rapidly, Europe, okay, China and Italy. I compare China and Italy, no? Because I am in Italy. So what we are doing in Europe, like in Italy, we are reducing a lot of our emissions. But what everybody else does, like China, is increasing enormously the emissions. Right now, China emits 29% of the world emissions. Europe, all Europe, 6.67%. So even if Europe go to zero and everybody else does not do that, it does not matter much. Okay. So what we see here is the emissions from China and Italy. Comparison between China. Italy is decreasing their emission, and China is increasing that. Now China is here, 10 tons CO2 equivalent per capita per year, 10, 11 tons essentially. Oh, and Italy is 6.7. So it's below China. So, and many other countries in Europe are in the same situation of Italy, okay? Italy is below average. So why we should do more? And China should still increase their emissions. So I see, so there is no sense. Do you understand well that there is no hope to decrease CO2 by looking at the coal station that are coal power plant that are built right now, this energy the global coal plant. So you see, in all Asia, they are building hundreds and hundreds of coal plant station, global coal plants. Okay, so producing electricity. So Europe is not doing anything. Okay, but China, India, Indonesia, Japan, Korea is doing everything. It's not doing exactly the opposite. Okay, so they are producing cheap energy for producing solar things to sell to Europe, no? CO2 emissions, you see Europe contribution, very little. Huh? China contribution, very large. A little bit more America, but this is situation. This is the world situation. Okay? Europe is not emitting too much. Okay? So is there. This is the cost and benefit of Paris climate targets. Okay, Toll has evaluated the cost and the benefits. The benefits of mitigating the climate using the zero emission scenario, so zero emission for 2050, are given by this curve. These are the economical benefits, okay, for mitigating the climate, as they would like to do. These are the costs for mitigating the climate. So you see here that the cost is far higher than the benefits. So there is no way. So this is the worst scenario. Okay, so we are assuming that the climate will change a lot, but the benefits will still be much, much lower than the cost. So zero. So this is the economic issue. Then, okay, we can do some ethical issue and say, well, we can change, we need to change, save the world, we need to save this, save that. So we need to use this new technology, green technology to save the world, blah, 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 and so on. Well, many people are analyzing this problem and they are realizing that there is no metals. There are no metals capable resources, no metal resources, to produce this green technology. Okay, all these things, no electric vehicles. So that means a lot of critical metals, as you see here. There are not. They are not. There are not. So simple. People don't find these metals. They are real metals, and so on. So we need a lot of these metals. They don't. Please not. They're depleting very rapidly. Okay, so we don't have. This is the level, and this is what we need. So we don't have resources. We don't have metals. Okay, to do this, and therefore, green technology may work for few people. So electric cars, few people may have it. Everybody goes with the horses. Electric cars, these are very nice picture. This is Italian electric cars, Dora, in 1907. Electric cars were the first one to be invented. Okay, and what happened to them? Okay, go to Wikipedia and you find the answer. What happened to the electric cars? Electric cars remained popular until advances in the internal combustion engine cars and mass production of cheaper gasoline and diesel powered vehicles, especially Ford Model T, led to a decline. Ice cars, much quicker refueling times and cheaper production costs made them more popular. However, this model came with the introduction in 1912 of the electric starter motor that replaced other of the laborious methods starting the vehicle and so on. So practically, they are telling us that the electric cars is old technology that is did not work. So compared to other much more efficient technology, which are internal combustion engine. And there is the problem with the batteries, for example, which is very problematic. Okay, of course, if we need to go to the moon, we need some electric vehicle. So for special cases, we can use this vehicle. But to think to substitute the entire car of the world with electric vehicle is simply insane. So simply, this is not possible. And there are no metals to create these things. So this is the end of my presentation. And I think that essentially there is no climate emergency. Therefore, these policies that Europe would like to do, and only Europe would like to do, are not justified by scientific research. Okay, are not justified. Of course, the climate will continue to change. Of course, humans are partially responsible for climate change. But we need to do the calculation very well. So we need to evaluate the cost and the benefit. We need to see what we could do with some new technology, or wait for better technology to come out. So we need to improve the cars. We can reduce the pollution, for example. That can be done with technology, improving technology. But we need to be careful not to not to propose things that will be much harmful. This green technology actually is very polluting, because it needs these metals that are not found easily, and therefore we will need to mine them, creating a huge amount of pollution. Okay, so and so on. So there is no emergency. So there is simply no emergency. There is an imbalance among the countries in the world. Okay, some are doing too much, others are doing too little. So and so on. So, and this is what scientifically, in my opinion, is. So there is no really climate emergency.